Today, I'm going to introduce a new video extension technology to everyone. Let me give a concrete example. I have a traditional 81 frame video here. After extension, as you can see, its length has been effectively extended, and in terms of color and video quality, there hasn't been much degradation. Of course, we can use a loop extension method to make it even longer. Take a look. This is after I extended the original video 3 times. This is the extended version. Later on, its overall color did show some degradation. For instance, an oily sheen started appearing on the face. However, its overall performance is actually much better than our single-frame extended videos. Here, a new model called Pusa is used. You can see its icon is a 1,000-armed Guanyan. This model is actually not a new one. We mention it because it has recently undergone a 1.2.2 extension. And Kijai Kashen has also implemented this model in ComfyUI. Regarding this model, I hope everyone grasps the following points. Firstly, this model makes video generation more accessible to the public. As you all know, training a model requires significant cost. On one hand, there's the financial investment for training, and on the other, there's the training data. For an image-to-video model like one, the training cost is approximately $100,000. Pusa's training cost, however, is only 1/200th of that, which is $500. Additionally, there's the training data. For an image-to-video model, it requires about 1/107 data points. But Pusa significantly reduces this by how much? 2,500 times. Therefore, it truly achieves more, faster, better, cheaper. Of course, I don't think this is a normal proposition. When we discuss all these data, we overlook a major issue. It is fine-tuned on models like 1.2.2, rather than being trained from scratch. Its technical innovation primarily uses a technology called VTA. Let's briefly explain this VTA technology. It essentially performs a vectorized adaptation in terms of time planning or layout design. How can you understand this? You can think of it this way. When each video plays, there is a progress bar that controls the mechanism of video generation. The Pusa model has a separate progress bar for each frame, allowing for more refined generation and frame-by-frame control. That's all for the concept. As we also mentioned, Kijai Kashen has already implemented this model in the One Video extension. You can open Kijai's One Video extension, then click on the example workflows. You can find such a workflow. This workflow is a concrete application of Pusa. Why do I say this? Pusa has a very important concept. It is a multitask master, meaning it's not just a model, but also a unified framework. It accomplishes many tasks, such as image-to-video, text-to-video, start and end frame generation, as well as video extension and video completion. Let me give you a heads up. Note that its quality, compared to the One model, has not fundamentally improved. If you want to achieve image-to-video, text-to-video, or even start and end frames, it's best to use the native One model. When using Pusa, we mainly utilize functions that are not present in the native models, such as video extension. The Kijai Kashen workflow you are currently seeing is actually a video extension workflow. Before using this workflow, you need to upgrade the extension version to the latest. Additionally, you need to download the corresponding models. These models exist in the form of LoRa. We can find these 2 models in Kijai's repository. Both models are about 1 GB in size, so the overall size is acceptable. Next, let's look at how this workflow runs. Please note, I have slightly refactored Kijai's workflow to make it easier for everyone to understand. First, there's the model loading section. I've divided model loading into 3 parts. Firstly, our corresponding configuration items. 2 technologies are used here: block swapping and model pre-compilation. For the high noise model part, we also used the aforementioned block swapping and pre-compilation. Then, when loading LoRa, everyone can see that the Pusa LoRa is loaded, which is a high noise model. Additionally, we loaded Light X2V. But please note, I'm using a different version than the original. I'm using Lighting T2V because I've tested a lot, and for a single extension, the difference is not significant. However, for multiple extensions, this LoRa model might perform better. It's best for everyone to test this themselves, as each person's environment is different, and the results might vary. After this, comes the main model. This is Kijai's 1.2.2 T2V high noise model. Similarly, I also loaded VAE here and saved the high noise model. We set up the low noise model. For this low noise model, note that we are loading the LoRa for the low noise model here. Some acceleration models have unified LoRa, so you can just use the same one. Okay, after the main model, let's look at the data processing section. We start with an original video. This original video was directly generated using the 12.2 T2V model. It features an ancient-style beauty dancing in a pond. After getting this model, we first scale it. So, I have some basic configuration items here. Let's briefly look at them. There's an overlap frame here. What does this mean? When we extend a video, we need a portion of frames, usually referring to the last few frames of the video, to serve as a reference. How many frames? I'm using 24 frames here. Below that are the total number of frames, and then width and height, which is our resolution. Firstly, we need to scale it according to the basic resolution. After scaling, I divided it into the last 24 frames and the first 57 frames. The last 24 frames are mainly used as a reference for subsequent video extension. I saved it. Similarly, we also saved the previous part. After getting the last 24 frames, we first perform a 1y6 extension, placing it into our latent space. Then, this part is crucial. Take a look. There's something called get latent size and count here, which is used to obtain some basic parameters from the latent space. Here we have a parameter, how many frames. But you need to note that this number of frames is different from the number of frames we mentioned before. Previously, we took 24 frames, but here there are only 6 frames. After obtaining them, we put them into a node. In fact, this is a basic configuration for video generation scheduling. Here, we also converted it into a float list. As you can see, this is a basic parameter required by Pusa when performing video sampling, scheduling. Then, the second very important node, please pay attention, is called onVideoAdd, etc. latent. Actually, it adds some reference latents to the basic latent space. Our basic latent is, of course, the empty one, so it's placed here. Then, our reference part is the last 24 frames we just mentioned. It's placed here. Then we get a new image embedding, and we save it. After that, we move into a relatively important section here. Take a look. The generation of image embeddings for high noise and low noise models. Here, we use a new node. This node is newly added in the new version specifically for the Pusa model, so it's called onVideoAdd Pusa Noise. Separately, we take the image embedding that was just generated and this float list, and use these two models to generate new image embeddings. One for the high noise model and one for the low noise model. Next is the sampling section. The sampling section is quite interesting. Firstly, let's look. There's a prompt here. Needless to say, this is the high noise model, and this is the image embedding corresponding to the high noise model generated here. Then, you need to pay attention to its sampling method. It doesn't use the coarse 4-step over 4-step sampling like in ComfyUI. Instead, it uses something called onVideoSigma 2-step. This means that we will infer a number of steps based on a parameter value of 0.875. This number of steps is not necessarily the first 4 steps or the last 4 steps. This actually simulates the generation process of 2.2. When we previously introduced 1-2 generation, we mentioned that it is an MOE mixture of experts model. What is the standard for switching expert models? It's the logarithm of the signal-to-noise ratio, and this value is 0.875. So, it implements this switching mechanism. Once calculated, we will know when this step ends and when this step begins. So, this is a different aspect. Please note the total number of steps. I set it to 6 steps, and I do not recommend everyone to arbitrarily adjust this number of steps. Why do I say this? Take a look. Here, there are 6 frames connected to the steps. Therefore, this should be fine-tuned by Kijai-Shen, generating 6 float lists using 6 sampling steps. So, I recommend using 6 steps here as well. Using more or fewer steps might cause some unpredictable effects on the results. This is the high noise model. Additionally, there's a shift value here. We can keep it at the default 5.0. And here, there's a new node called onVideoScheduler. This is a separate implementation of the scheduler. Here, it specifically schedules for the Pusa model. The key is that the scheduler selected is flow match Pusa. Similarly, this is the low noise model. The basic settings are the same. The only difference is that the start step and end step for the two models are different. Now, let's look at the generated effect. This effect is very good. Similarly, we can extend it further. I've added a loop structure here, which is what we often use for loop start and for loop end. Firstly, we connect them with flow, representing that they are a whole. And here, I also added a loop count, which determines how many times we loop. The previous one was a single loop, but sometimes when we extend, it's not necessarily just once, it could be multiple times. However, if you use multiple extensions, the model quality will continuously decline. As long as you perform this kind of extension and use acceleration, this is unavoidable. It cannot completely solve such a problem. We just need to see if the degree of degradation is acceptable to you. First, take a look. I gave the resized model to a variable inside our loop, which is initial value 1. Inside the loop, it becomes value 1. After that, it will separately retrieve our last 24 frames and first 57 frames, which are a total of 81 frames. The subsequent operations are essentially the same. After that, I will feed the generated result. This result is what we've combined back to initial value 1. So, through the loop, I can perform multiple extensions. The basic mechanism is like this. Of course, there are some other differences. For example, here, I originally directly used the length of the original video. Now, you can't use the original video's length. You can only use value 1s. Regarding this workflow, you just need to look at the differences. Then, since I performed 3 extensions here, let's verify how much the effect degrades after 3 extensions and whether it's within our acceptable range. In the early stages, there are no problems. However, as the extension deepens, you will find that the color saturation will slightly decrease. Additionally, an obvious oily sheen effect will appear on the face. Another issue is that as the extension increases, the overall movements will also become less pronounced. Therefore, we believe that extending a video 2 or 3 times should be the limit. Do not perform too many extensions, otherwise, the quality will significantly drop later on. Okay, that's what we wanted to share with you today about this new model. What are you waiting for? Go ahead and try it yourself. Follow me to become someone who understands AI.